Hi, and welcome to today's lesson. Today we're going to be speaking about vectors in two dimensions. Before we get going, I think it's important to break up this word, or these words, to see exactly what we're going to be speaking about today. So firstly, let's see if we can remember what vectors are all about. In grade 11, you would have learned that vectors are physical quantities which have a magnitude and direction. And vectors are usually written with a little arrow above the symbol. So examples of vectors would be a force. Let's call a force F. And the way we know that it's a vector is if it has a little arrow on top. Other examples of vectors are things like velocity, acceleration, displacement. So those are all examples of vectors. And the key thing about vectors is the fact that they have direction, unlike scalars, which only have magnitude. The way we represent vectors, as you'll remember from last year, is with an arrow. So we'll draw something like that, where the length of the arrow indicates the magnitude, and the direction of the arrow with respect to another direction gives us the direction of the vector. So you'll remember all of this from last year. The only difference is that in grade 11 you have to worry about vectors in two dimensions now. So what does this word dimensions mean? Dimension, as you'll know, is sometimes used to describe a size or a length of a box or a piece of paper or a distance on a ruler. So when we speak about one dimension, we speak about pretty much a line. So one dimension means moving along one line. When we speak about two dimensions, we say, okay, one line, but you can also move up and down. So a line would represent a one-dimensional object. A piece of paper, a really thin, infinitely thin piece of paper, or any geometric shape really, would represent a two-dimensional object. And as you know, a three-dimensional object would have 2D plus an extra dimension. So what does this mean in terms of vectors in particular? Well, in grade 10, when you did vectors in one dimension, which means if you have your house, for instance, over here, and you had the shop conveniently along the same road, and you worked out the displacement, it was along a straight line, either to the right or to the left from how we're looking at it now. But now we're in grade 11 and we're moving on to two-dimensional. That's two-dimensional, three-dimensional, one-dimensional. So now we're moving on to two-dimensional vectors. So that means basically you can move along one axis or another axis. And that just gives a lot more freedom. And obviously everything in the real world is 3D. So that's just kind of the natural progression that you're going through at the moment. So at school level, grade 11 and 12, 2D is what you have to worry about. So I said in the beginning that you describe vectors using arrows, right? An arrow where the magnitude is the length, magnitude is represented by the length of the arrow, and the direction is usually an angle to something, to some kind of axis or perhaps even another vector. Now you may be thinking, what is the use of a vector? especially why are we worrying about them now in 2 dimensions? Well, let's take an example of a box and pretend we're looking at it from the top. Okay. And we have a certain path that we want to push this box along. So we have 2 people pushing it. This is a view from the top. So one person pushing that way, one person pushing that way. And what we have, this is just a redrawing, is a force like that and a force like that, right? We're pushing, we're exerting a force. Force is a vector. Call this one F1, F2. So both forces have magnitude and direction. The guy on the left is pushing a bit harder than the guy on the right because the left hand length of the arrow is longer than the right hand length of the arrow. So if you wanted to know what is the overall force forcing this box forward, right? Because some of this force here from the left hand side guy is pushing it forward. Some of this force here is also pushing it forward. So what is the resultant of these 2 forces causing this box to move forward? So that's just a simplistic explanation as to why we need vectors. In real life, it's a lot bigger than that, and vectors are one of the most useful mathematical constructs that we have. So to begin, we want to know how to add vectors. I'll mostly be using force vectors, F1, F2, etc. For no particular reason. You could use other vectors such as velocity or displacement, or really any other vector that suits your taste. But I'm primarily going to be using force vectors just to keep consistent. It doesn't really matter. You can think of them as just arbitrary vectors. So we want to know how to add 2 vectors. In your textbook, it'll probably explain things like the parallelogram method, adding vectors at right angles. But I find that all of those different methods seem to confuse students, even though ultimately they're doing the same thing. So the way I would like to teach it is using something called the head to tail method. So before we get started on adding vectors, let's just go over the concept of a coordinate system, and then we'll get to the head to tail method. So because we're dealing in 2 dimensions, we have to have 2 coordinates describing our vector. What that means is, most of the time, we'll be dealing with an x and a y. It doesn't have to be an x and a y. A coordinate system to which our vectors can be placed relative. So that can be x, that can be y, and this can be a vector, right? Calling it f, it could be acceleration, it could be velocity, it doesn't matter, anything that's a vector. Now, because we have a coordinate system, we can describe this vector. Firstly, its magnitude is its length, so that's fine. But how do we describe direction in real life? If I'm standing and facing you, and I say, there's something on my left, it's on your right. So direction is relative to something, right? That's why we choose a coordinate system. So, for instance, if we said this forcing vector is 30 degrees clockwise from y, we could easily say also that the force vector f is 60 degrees anti-clockwise or counterclockwise from x. So we just use coordinate systems to describe our vector and its position. Sorry, more so its direction. So coming to adding vectors now that we've established what a coordinate system is and why it's relevant, let's start off with a simple example where we want to add 2 vectors. Let's say we want to add this vector, we can call that, let's get away from the forces, let's just call that vector A. And let's give it a magnitude 5, just a random number. And we want to add another vector going that way. In this particular example, this second one is at 90 degrees or perpendicular to the first one. And we call this vector B equals 10. Right, I'm not too worried about the units right now. This could be newtons, it could be meters per second squared, meters per second. What it is doesn't really matter. We're just trying to explain the concept of adding vectors. So how would you go about adding these vectors? Well, we use something called the head-to-tail method. And it's pretty universal for vectors. When I say pretty, I mean definitely. Right, head to tail method. Right, as you'll remember from grade 10, the back of a vector is called the tail, and the front, you guessed it, called the head. So if we wanted to add this vector to this vector, what we do is we line them up almost like elephants lining up when their trunks hold the other one's tail. We line up the vectors head to tail. So it doesn't matter which way you start. You could start with the B and then attach the A to it, or you could start with the A and attach the B to it. I'll show you both methods. Let's start with the A first. So we have that A, which is 5. Okay, going straight up. And then we take that B. We take this guy here. And we put its tail on A's head. Like that. Alright, so we just set them up like that. And then what we say is, well, we know this is 5. We know this is 10. To add these two vectors now, what we do is we take the very beginning, the very end, and we go from the beginning. Let me just choose a different color for this. We go from the very beginning to the very end. And that is the net vector. Okay, that's what happens when we take the vector 5 going up plus the vector 10 going to the right. We get this here. Okay, and keep in mind that this magnitude is not 15. You can't go 5 plus 10 equals 15 because we're dealing with vectors. So all of a sudden, you'll realize that this becomes a bit of a trigonometry problem, right? Because we have a 90-degree angle there. So how would we work out the magnitude and direction, right? Because vectors have magnitude and direction. And when we calculate a vector, we need to determine both its magnitude and direction. How do we calculate the magnitude and direction of the resultant vector? Well, the first thing we do is get the magnitude. And we know because this is a right angle triangle, right? In the beginning I said A is perpendicular to B. Because this is a right angle triangle, we can use our friend Pythagoras. And conveniently, Pythagoras says that A squared plus B squared is equal to C squared. And what does this mean in terms of a triangle? If this is side A, this is side B, this would be side C. Okay, C is the hypotenuse, the longest side of a right angle triangle. So to calculate C in this case, C squared we'd say is equal to, we'd take A and square that. So we know A is 5 squared. We'd take B, which is 10, and square that. Then we get rid of the squared on the left-hand side, right, by square rooting both sides. So if we're getting rid of that squared, then we have to say C then is equal to the square root of 5 squared plus 10 squared. And I'll give you a few seconds to work that out. Well, I work it out also. And you should get to the answer of 11.18. Okay, so that's great. So now you have the magnitude, which is represented by the length of this vector, to be 11.18. Great. Equals 11,18. But remember, you're calculating a vector, right? So what you need to do is you need to find out what this angle is here. So that you can say, well, the answer, okay, let's give the answer a name. Let's say over here, we said A plus B is equal to, let's just say D. So we don't get confused with C being the magnitude. All right, is equal to D. So if we get the angle relative to this guy over here, this 5 upwards, right, the vector A, then we can say D is equal to magnitude 11,18 at an angle relative to this, right, this angle here. So as long as we give our answer relative to something that we know the direction of, that's fine. Question is though, how do you calculate this angle here? Let's call this theta. How do you calculate theta? Well, you know from trigonometry, I'm not sure if you'll use this acronym or abbreviation, SOHCAHTOA, right? Sine equals opposite over hypotenuse, cos equals adjacent over hypotenuse, and tan equals opposite over adjacent. Okay? And that's obviously sine of an angle, sine, cos of an angle, tan of an angle. So if you know two of the sides of a right angle triangle, you can work out any angle within that right angle triangle. And we do. We know all three sides. We know the two we were given, right? 5 and 10. And we calculated the hypotenuse to be 11,18. But let's just use what we're given, just in case we calculated the hypotenuse incorrectly. It's always a safe way to go about it, even though that is right. So we know, relative to this angle here, the adjacent and the opposite lengths. Okay, adjacent and opposite, so can't use that one. Can't use that one. We will use tan. Okay, so we'd say the tan of theta is equal to the opposite, which is 10, over the adjacent, which is 5. So then you'd go theta is equal to tan to the minus 1, known as the arctan function, the inverse of tan, 10 over 5. Usually on calculators you'll have to push second function and then tan to get that. Right? So when you take arctan, or tan to the minus 1 of 10 over 5, or 10 over 5 is 2, you should get 63,43 degrees. Now you have a magnitude and a direction for this vector. So at the end of the day, you can say the overall vector d, or the sum of those two vectors, right, a plus b equal to d, d is equal to a magnitude 11,18 at an angle of 63,43 degrees. Okay, but you need to say relative to what? Because that could be 63.43 degrees relative to north, if we're talking about a compass, or relative to west, if we're looking in the westerly direction. So relative to, or better yet, we say clockwise from A. right? Because that's where we defined our angle from. We took A and we said, okay, we're going to go clockwise to get our total vector. So that's how you add vectors in 2 dimensions when they're at right angles to each other. Now you may have noticed some of the words I used for that overall vector. This guy over here, which is our overall vector, represented by D. You may have noticed I used the word sum vector or total vector or net vector or resultant vector. Now all of these things mean the same thing. These are probably the most common ones, net and resultant. Those are often what you speak about when you add 2 vectors or subtract 2 vectors from each other. You'll speak about the net or resultant vector. So to round off this lesson, just to summarize what we've learnt, right, revision-wise, vectors have magnitude and direction, which is super important. Emphasis on the direction. Okay. Emphasis on the direction because when we add 2 vectors together, the net vector obviously then has magnitude and direction. Okay, so that's really important. When adding vectors that are perpendicular to each other, so when adding 2 perpendicular, right, that simple means perpendicular, vectors, we use Pythagoras, okay, to get magnitude. Okay. And then how do we get the angle? We use trig to get the angle. Okay, using either sine, cos, or tan. It's usually most of the time it will be tan, but you just have to see what sort of vector triangle, right? Which is the sketch. Yeah, I'm using a term there that you may have not have heard. That we call this a vector triangle, right? Because obviously it's in the shape of a triangle. So whatever your case is, that's what we'll use, either sine, cos, or tan. So the next lesson will cover what happens if those vectors are not nice and perpendicular. What if we have a vector like that and a vector like that? What do we do? We'll speak about things like components and other exciting stuff. But thanks for listening, and see you next time.